do this real quick. So just remind you that we know how to now calculate magnetic fields. So the way we calculate magnetic fields is, hide you guys for a second. So again, we have Faradays Law, which says that the magnetic field then is equal to mu naught I divided by 4 pi integral dl cross r hat divided by r squared. Ampere's law, which says then that the closed loop integral of the magnetic field divided by the differential length is equal to mu naught times I enclosed, where again, in general, I enclosed is going to be the integral of the current density integrated over the area. The last example we saw of this guy was the solenoid. So here we found that the magnetic field of the solenoid is equal to mu naught times little n, where little n is big N divided by L, where big N is the number of loops. L is simply the length. So this is the number of loops per unit meter, or per unit length, times the current. And then what we focused on mostly last time or yesterday was looking at applying these magnetic fields that we found using these guys to now back to the force. So again, force on a straight wire in an external magnetic field, which is constant, is IL cross B. Or if I have a non-straight wire or a non-constant magnetic field or both, then that's equal to the integral of the currents integrated over the differential length cross that by the external magnetic field. Or if I have a charged particle sitting in an external magnetic field, then here the force on it is the charge of that particle times the velocity crossed by the external magnetic field. So far we did examples of this guy, right? We're gonna do one more, or sorry, no more examples of this, but you guys are gonna have a group assignment on this. And we primarily looked at the force between parallel wires. So here we found that the magnetic force on each one of these two wires is given by mu naught I1, which is the current through the first wire, times I2, which is current through the second wire, times the length of the wires, where here I'm assuming the two wires have equal length, divided by 2 pi d, where d again is that center to center separation between the two wires. Now, most of the time it's going to tell you it's a wire which has a current that are separated by distance, so you're not going to be too worried about the center to center distance. It's just the distance between the two wires. So again, just to remind you, we found that if the currents were in the same direction, that was an attractive force, but if the currents were in opposite direction, then that was a repulsive force. So we're going to do one more example right now, which focuses on now this one, which is the force on a charged particle moving in an external magnetic field. So let's look at that example. So where's my example? So here it is. So this one says we have a long solenoid, which has 100 turns per centimeter. So this is little n, and carries a current of I. So an electron moves inside of the solenoid in a circular radius of 2.3 centimeters perpendicular to the solenoidal axis, which is the direction at which the magnetic field points. And then it says the speed of the electron is equal to 0.046 times c, where c is the speed of light, which is given as 3 × 10⁸ meters per second. And we want to know in this case, then, what is the current responsible for this thing to have this particular radius? So basically what's happening here is I have a charged particle with a velocity initially perpendicular to the external magnetic field, which means, as we talked about before, this thing is going to move under uniform circular motion. So here we know the radius, we know the velocity. So from here we can then determine what the current is. So let's draw our problem. So let's draw what this thing looks like. So here, this is from the front view. So front view. So basically what's going to happen is here is my solenoid. Okay, so this thing has some radius where I'm just going to call this radius r, where radius r is greater than little r, which is the radius of that uniform circular motion, which was 2.3 centimeters, right? So on the inside of here, what I have then is what? An electron, which is moving under uniform circular motion at this radius of little r. And let's say, for instance, it's here. So this is my electron, and it's moving with an instantaneous velocity in this direction, where that velocity is given by 0.046 times c, where again, c, we'll talk about this after the next exam primarily, is the speed of light, which is equal to 3 × 10⁸ meters per second. This is what we call the speed of light. It's actually a little bit below this. It's like 2.998, blah, 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 but we're going to call it 3 × 10⁸. So speed of light. So one nice thing is whenever you have a problem, especially on an exam, and you need to find the velocity of a charged particle, and if you find it greater than 3 × 10⁸ meters per second, something went wrong somewhere. Okay, nothing can ever travel faster than the speed of light. Actually, anything with mass can't travel at the speed of light, so it has to be always less than this number. So that's a good kind of check. Okay. So basically what's happening here is, again, this thing is creating a magnetic field. This guy is moving in a circle, right? So we can determine the direction of the magnetic field. So in this case, we know the force has to be towards the center. So this thing is feeling a centripetal force towards the center. So let's actually determine the direction of the magnetic field. So here we would have to put our fingers in the direction of velocity, curl towards the direction of the magnetic field to have our thumb point in the direction of the force, which means in this case, I don't want my magnetic field pointing inward to get my force to point in this direction. However, what is the sign of the charge of an electron?
Negative.
Negative, which means that we actually have to do an extra 180-degree rotation, which means for the electron, we'd actually want our fingers pointing in the direction of velocity, curling towards us. So our thumb would point away. And then because of the sign of the electron, we'd have to rotate then by an extra 180 degrees to get the force pointing inward, which means that the direction of the magnetic field in this case is actually going to be out to the page. So right-hand rule number 3 says we'd have to curl our fingers in the direction of the current to get our thumb pointing towards us, which means this thing has a current, which is going in the counterclockwise direction. So this is our current. So basically what we want to know is what is the magnitude of this current to get this electron to move in uniform circular motion of this particular radius of 2.3 centimeters. So good. So let's write this out. So here we know that we have the sum of the forces acting on our charged particle is then equal to the centripetal force, which is then mv squared over r, right? This thing is moving in uniform circular motion, so this has to have the centripetal acceleration. The only force acting on this thing is actually the magnetic force. So here we have the magnetic force then is the centripetal force in this case. Now here, since this is a charged particle moving in an external magnetic field, then this thing is going to be written as the charge, which we already know is an electron. So let me write that as E actually. So this is going to be E times the velocity times the magnetic field, which in this case, what's supplying the magnetic field is the solenoid, times the sine of the angle between the two is then equal to mv squared over r. Now, in this case, the velocity is anywhere in this plane while the magnetic field is perpendicular to this plane, which means what's the angle between the magnetic field and the velocity? So if the velocity is anywhere within this plane, magnetic field is pointing perpendicular to that plane, what is the angle between the velocity and the magnetic field anywhere?
90.
90, good. So this is going to be 90 degrees. So this is simply going to be then the electron charge, which is the fundamental charge, times the velocity times the solenoid magnetic field is then equal to mv squared over r. Okay. So from here, this velocity is the same as this velocity, so one of those are going to cancel out. And we also know from the previous page that the magnetic field of the solenoid is simply equal to mu naught times the number of loops per unit length times the current. So let's plug that in. So this finally becomes the charge of the electron times mu naught times n times I, then must be equal to mv over r. So from here, we can finally solve for the current. So this thing tells me then that the current is then equal to m times v divided by e mu naught n r. So this is my current. Here, the mass is the mass of the electron. So just to remind you, the mass of the electron is equal to 9.11 times 10 to the minus 31 kilograms. Charge of the electron is equal to 1.602 times 10 to the minus 19 coulombs. Mu naught is equal to 4 pi times 10 to the minus 7. So these are all my constants. Here, again, V is just 0.046 times 3 times 10 to the 8th. R is 0.023 in meters. Plug in our numbers, we find in this case then is this works out to be 0.272 amps. Let me write that up here. So the current then works out to be 0.272 amps. after we plug in our numbers. So this is the current that we need running through our solenoid to make this thing actually then move with a radius of 2.3 centimeters. So quick question, what would happen to the radius if I decrease the current? So if I decrease the current and I made it less than 0.272 amps, what would happen to the radius? Would it increase or decrease?
Decrease.
It would. Was that decrease or increase? Sorry, Bill.
Oh, if you decrease the current, you decrease the velocity.
Well, you don't change the velocity. What would happen to the radius? Because the velocity is fixed by how fast the electron was originally moving. So I want to know if I decrease the radius, or sorry, decrease the current, that would make the magnetic field go down. And then what would happen to the magnetic force? That would also go down, which means what would happen then to the radius? The radius then would have to increase in this case, right? So the smaller I make the force, the bigger the radius then is going to become. Good. All right. So good. So that's the last example problem we got for you. So from here, we're then going to give you guys a group assignment. Give you a few minutes to kind of work on this. So this has, we have a long straight wire. That's this top one here, carries a current to the right, which is equal to 30 amps. Below that is a rectangular loop, which has side lengths of this length across here, which we're calling L, or this length down here, which is 30 centimeters. And then this length across here, B, which is the two sides. This is then 8 centimeters. And this guy is going to carry a current in the clockwise direction, a current of 20 amps. Okay, so this one has 30 amps. This one has 20 amps moving in a clockwise direction. And then the straight wire is separated from the closest side of the rectangular loop by 1 centimeter. So that's what this A is here. So wants to know in unit vector notation, which I just wrote upward here, because unit vector, if I call that the y direction, then this would be in the j hat direction. But anyways, we want to know what is the net force acting onto this loop due to this guy. So what I have here is I have what? A loop of wire, again, carrying a current. It's in an external magnetic field, which is created by wire number 1. Okay? So I have the force on a wire in an external magnetic field created by another wire. So basically what I can do from here is what? Calculate the force on this wire, force on this portion of the wire, force on this portion of the wire, and force on this portion of the wire. And then the total force on this loop then is simply equal to the vector sum of those 4. Right? Now, let's talk about this portion here and this portion here. Now, technically, remember that the force on a wire, or sorry, the magnetic field created by a wire is position dependent, which means it gets smaller the farther you go away from it. Remember, so the magnetic field from a straight wire is mu naught I over 2 pi r, which means the closer I am to the wire, the bigger the magnetic field is, and the farther I am away, the smaller the magnetic field is. Which means technically, if I wanted to find the force on the 2 pieces of side length B, you would have to then integrate over each one because it's in a non-constant magnetic field. But what can you tell me about the force on the right portion versus the force on the left portion? What's going to be true about the force here versus the force here? What do you think?
They're going to be the
They're going to be the same, but keep going, Derek.
opposite.
Opposites. So even though I would have to integrate over this guy and integrate over this guy, but the force on this guy will be exactly the same in magnitude as the force on this guy, they're just going to be opposite directions, which means that the net force on here, this portion is going to cancel this portion, so they're just going to go away, right? The vector sum between this and this is going to cancel, which means the vector sum is only going to be from the top wire and the bottom wire. But as we said, the magnetic field up here is stronger than the magnetic field down here, which means the force on the top part will not be the same as the force on the bottom part, which means that these two will not cancel as well. Right? So there will be an overall net force on this. Now for here, anywhere across this line, since it's at equal radius, that means the magnetic field across here is constant, And since all this is at equal radius, all the magnetic field down here is also constant, which means for this portion and this portion, you don't need to do an integral. You just have to find out what the magnetic field is at those parts. So that's about it. So from there, just calculate the net force on each part. Use your right-hand rules to determine, or the fact that if you have two parallel currents in the same direction, that's attractive. If they're in opposite direction, that's repulsive. Either way is sufficient for these guys, but yeah. So go ahead and work on those. I'll do the same thing as last time. I'll split you up into breakout rooms. Did you guys like the breakout rooms last time? No. Maybe. You guys are so quiet today. Okay, so let's make some breakout rooms. Good. So let's do. So if I do, oops, not one breakout room, that would be ridiculous. Okay. There we go. So let's do about 6 or 7 rooms again. Let's do 7 rooms. Right. And then again, I'll come around, check on all of you. Give you about 15 minutes. It won't take that long, and then from there, we'll start the next chapter. So have fun. And don't forget to join the breakout rooms. What am I doing? Let me close this. How are you doing so far?
So far, so good.
Good. You guys are awfully quiet today. One of those days we didn't want to get out of bed. Pretty much.
Yeah.
All right. Well, if you guys are okay, then I'll go away and I'll come check back on you later.
I think it's just like that current thing, right? Where it's like U naught times both the currents.
He said the I2 would be greater than, or the coupling would be greater.
Okay.
That traction current. I don't know.
How are we doing here?
You said the two side forces are going to cancel, right? And then
Correct.
it's just going to be the top and the bottom.
Correct.
Okay.
So yeah, it'll just be the vector sum of the top and the bottom. But since the currents are moving in opposite direction, then that means the force on the top will be in the opposite direction as the force on the bottom. So you just have to subtract those two.
Yeah.
And you're correct. What you were saying when I came in, then the force will be mu naught, current times the first, times current times the second, times the length, divided by twice 2 pi times the distance.
Is it always the same equation then?
Pretty much.
Like just as long as
Unless the 2 wires are not parallel, if they're kind of like at an angle, then you would have to do something slightly different. But yeah.
Okay.
Yeah. But here they're parallel to each other. So yeah. So that equation is still the same.
All right. Thank you.
Correct. Correct. He's doing okay. Not too bad. All right. I'll go join somebody else then. Have fun. How are we doing here?
Hey, it just let me in here. It said I was in like a joining type
Oh, really?
thing. I couldn't hear anybody or see anything, but
Gotcha. So you were in limbo for a while? Gotcha.
I guess, yeah.
Okay. For those who have been here, how are you doing? Gotcha. That doesn't make it convenient. Okay. All right. Well, let me know if you have any questions. I'll go check on everybody else. I'll be back.
All right.
Go to. All right. How's everybody doing here?
I think we're doing all right.
All right.
For some reason, though, I get a 3.2 times 10 to the negative third instead of fifth.
That might be true. I think I might have a typo here. Yeah, I think I might have not converted the distances correctly. So yeah.
Okay.
Yeah, I just got that too. So
Yeah, so I think it's actually -3. I'll have to change that one of these years. So it'll be fine.
Or just let them correct it again next year.
Exactly. Can't be perfect all the time. What can I say?
Yep.
Nice. Okay, so it sounds like you guys are doing good. All right, I'll go check on somebody else. You guys all. Let's go here. All right, how are we doing so far?
I have a quick question.
Sure.
So for this one, all I did was use the like the loop equation, you know. I forgot the name. But like the one we went over in class yesterday, where it's U naught times I1 I2 L over 2
Oh yeah,
ID.
yeah, the force between parallel wires. Yes, correct.
Right. And so then I just subtracted the top one from the bottom one.
Yeah, because in the one case, the two currents are in the same direction, so it has to be attractive.
Right.
And for the bottom part, they're in opposite direction, so it has to be repulsive. That's correct. Yeah.
So is that? Can you do it that way? I mean, because I got the right answer, but I got 3.2 times 10 to the negative 3. So
Yeah, it should be
I'm trying to
-3, not -5. I think I wrote this, I think 2 or 3 years ago, and I forgot over 2 or 3 years to change that to -3. I think I didn't
Okay.
change the centimeters and the meters when I wrote down that answer. So yeah.
So was that the way you were wanting us to do it or not?
Yep. No, that's it. Yep.
Okay, perfect. All right. Thank you very much.
You're welcome. All right, let me go check on other people. I'll be back.
Well, yeah, okay. So the reason that W and Y are going to cancel is because they don't have that like additional, well, okay, with the box on the bottom, it says I2. Do we just assume the current's going through all that? Is that all a big wire?
Yeah, that's all a big closed
Oh,
circuit
okay.
wire. Yes.
Okay.
Yes.
I didn't even realize he joined us. He kind of scared me.
All of a sudden, the booming voice started scaring you. Yes, I'm haunting you in your dreams as well. So.
Mhm.
I think we missed why the vertical sections of the wire loop cancel each other.
Oh, so because in the one case, so if you look at the right-hand one, the current is going downward, right? But the magnetic field is into the page since the current from the wire is going in this direction. So on that side, you'd put your fingers down, curl towards, which means the force would be to the right.
Gotcha.
And on the other side, the current's going upward. So that means the force is going to be to the left. So the force is just in the opposite direction.
Gotcha.
And
Okay.
since you're integrating over the same R positions, so the magnetic field is changing the same over each portion of the wire, and they have exactly the same amount of length, and that means the magnitude of the forces are the same as well.
Gotcha. Okay.
That's right. But for the top portion and the bottom portion, since the external magnetic field is non-constant, the closer you are to the wire, the bigger the magnetic field. That's why those two don't cancel.
That makes sense.
Okay.
Sounds good.
Yes, thank you.
You're welcome. All right, let me go check on some other people. I'll be back. Good morning, sleepy faces. How are we?
Hola.
I woke up 30 minutes ago. So
That's not bad. That is actually not bad. 5 minutes before class, that works. So how are we doing here?
I'm about to plug this in my calculator. Hopefully it's right.
Okay. So one thing is the answer I have written down is wrong. It should be to the -3, not to the -5. So,
Got it.
but the prefactor is fine. So the 3.2 or whatever that is. So.
So this problem would just be the equation for the parallel wires. It would just be that minus that equation again, right?
Exactly.
Okay.
Yep, just two different distances. So the one distance is A and the other distance is A plus B. So. That's
Okay.
it.
Okay. I got you.
Yep. Doing okay?
Yeah.
Yes.
All right.
Thank you.
Sure. All right, I'll leave you back to your slumber. I'll be back. All right, how we doing, gentlemen?
Pretty good, I think.
Good.
I'd say better than last time you stopped in.
Good. So just know the answer I have written down should actually be 10 to the -3, not 10 to the -5. So in case you're getting that, yeah. So it should be 10 to the -3 instead. Other than that, everything is going okay? So far so good. Good. All right, I'll be back.
Static? Yeah, it is.
Yeah, it's good.
He's doing okay?
Yeah.
Yep.
Got
Yeah.
the answer.
And you got the -3, not -5?
Yeah.
We all make mistakes sometimes. It's fine. All right, so I think most groups are almost done. So probably be here just for a few more minutes and then we'll go from there.
Okay. How
I
many
think
more?
your camera's frozen. You're just staring at me.
Yeah.
The same way. Nice.
How many chapters do we have left?
For this exam?
Yeah.
Technically one.
Just one.
So that's the one we're going to start today. So yeah, so this previous chapter here was quite long, if you notice that much. So we're going to start chapter 30 today. So technically it's only chapter 30, but if we end up a little bit ahead, I might add AC circuits to it as well. So, but we'll see how things kind of go in the next few days. So
We're doing AC capacitors right now.
oh, nice.
And circuits, and it's like so much different than like what we're used to, like where you taught us capacitors, and
Yes.
I don't like it.
Yeah. So yeah. So there you need to know if what the current and the charge either lag or are ahead of the AC power source, or if they're the same.
Yeah. It's like thinking of like the voltage as like a system of time or like a function of time.
Correct.
And it's like
Yeah,
dependent.
because it's a sinusoidally oscillating system. That's right.
We're actually like using integrals and derivatives now, and I'm just like, I don't want to do this.
Gotcha. Nice.
So
Yeah. So if we have enough time, we'll do that first, going into the exam, because that's only about a day or two to spend on that. So not too bad. We don't do too much with that. But we do have to integrate or introduce phasers. Have you guys introduced phasers yet, or no?
No,
No.
I don't think we do to the end of the semester. Like we're doing capacitors and inductors and then RC circuits.
Okay. Gotcha. So RC with AC or just RC in general?
RC with AC.
RC with AC.
Yeah.
Yeah, we won't spend too much time on it, but we'll talk about it a little bit. So
It's kind of cool because like we're learning about the magnetic fields and stuff would be like with capacitors and electric fields, and I'm actually understanding what we learned before better now, because like I'm actually understanding the fields a little better.
Good. Very good. Yeah, soon we'll chapter 30 we'll start talking about inductors. So we'll spend on a lot of time on those. So.
I think we start those. Well, she wants to start them tomorrow, but we haven't even learned like all of capacitors yet, so I don't know what's going on.
Okay. Gotcha.
So
Nice.
I don't know. I'm still looking into that boat idea with capacitors now, but I'm working with I'm trying to talk to Dr. Cuban about it
Okay.
and try to figure it out with a bunch of the other like senior design people.
Yep. Talk to Deersing as well. I mean, he is the electrical engineer person there, so I would say probably talk to him as well. See what he says about it, but yeah, my only concern with that is I think it'll increase the potential, but also because the capacitors stop the flow when they get fully charged. So you might have to hook them up as a different routing type system instead of having a system. But
me and one of the seniors were talking about that, how we're going to hook them up in series and parallel and how it might affect certain things.
Right.
And we weren't for sure how we were supposed to hook them up.
Gotcha. Okay. Yeah, I haven't had time to think about that yet, but I'll try to do that soon.
No, you're okay. I'm just like we won't be done for another few months anyways. Like we still haven't even started building it. We're just working on new ideas and stuff because last year we didn't actually get to build the boat, so we have no idea what's going on because all the seniors graduated. So
Gotcha. All right, let me check on these other groups quickly, and then we'll reconvene.
Okay. All right.
So where am I now? Okay, good. I'll be back. All right, how we doing here? Guys doing okay? Maybe. No. Okay. I'll be back. All right, welcome back slowly, everyone. So it sounds like everybody was fine with that, so that's good. So that concludes chapter 30. So now we can actually start working on the next chapter for the exam. So it's going to be chapter 30. So it's chapter 29. So now we're going to do chapter 30. So basically, chapter 30 wants us to ask a question of, is there a relationship between the electric field and the magnetic field? So is there a relationship between the two fields that we now know? So between our electric field and our magnetic field, right? So this is the question that it wants us to basically ask. So far, what we've seen is we've seen all electric, right? We have static electricity, we have all that good stuff. We have magnetism. So for a long time in physics, there was actually electric theory and then there was magnetic theory, and these two things did not actually talk to each other. And the reason they didn't talk to each other was, for example, if I had a positive charge, so say here's my positive charge, we know this thing has an electric field. So here's our electric field pointing in straight lines, something like this. If I brought a compass near this charge, it's still going to point in the direction at which it was pointing, right? So if my north was pointing here, but if it was started off with my compass pointing over here, the north side never actually changes when I bring my compass from this location to this location, which basically would imply to us that there is no interaction then between the charged particle and the magnetic field of the compass, which means there would be no interaction between the electric field and the magnetic field, right? Because we know this guy has its own magnetic field, where his magnetic field is doing something like this, right? This is just a bar magnet. So this is our magnetic field. So this would imply that there's no interaction between the two. However, if I took that same compass and I brought it near a current carrying wire, so here's my current carrying wire, moving in this direction, let's say my current is moving here. So again, then when it was over here, the north side would be pointing in this direction. However, if I brought the compass near then the magnetic field, of that of the wire, so my magnetic field is curling around in this direction, my compass needle then is going to point in the direction of the magnetic field of the wire. Right? So in this case, this is creating magnetic field. The compass also has its own magnetic field, so there's an interaction between the two magnetic fields. However, what is current though?
Moving charge.
Moving charge. So that means each one of these moving charges, which is inside of the wire itself, so here if this is my moving charge Q, each one of these Qs has their own electric field. So what this guy actually implies is that what? The magnetic field, which is created by the moving current, by the moving charges, is actually a manifestation of the fact that the electric field itself is moving. So what's really happening is that a time-dependent electric field is actually generating a magnetic field. So this is actually what this would actually imply to us. So this experiment then, or at least this knowledge would basically imply to us, well, there should be some sort of interaction or relationship between the electric field and the magnetic field, because it's actually moving charges constitutes a moving electric field. That moving electric field then creates our magnetic field. So this, looking at the wire, would imply to us that, well, yes, there has to be some sort of relationship between the two. This one tells us no. This one actually tells us yes. So the overall answer, as we're going to find out, is actually the answer is yes. There is a relationship between the electric field and the magnetic field, and that's what we actually want to figure out in this particular chapter. So what is the relationship between these? Now we're going to look at only part of the relationship, and then after the next exam, we'll continue this relationship and then see the overall relationship between the two. And it turns out that the relationship between the electric field and the magnetic field is what sources light. So actually this relationship is what is the source of light. So without this relationship between the two, we would never have electromagnetic radiation. We wouldn't have light, which means we wouldn't be able to see anything, which means we have zero information about things, and our life would be kind of sad. We wouldn't be able to see anything. Still be able to hear things, but wouldn't be as fun. So good. So to figure out how this actually works, we're going to look at a couple experiments here. So I'm going to let other people do this because I haven't been allowed on campus all week, so I can't actually make videos. So there it is. So let's look at a couple of these and kind of see what's happening. So this first one is from Purdue. So let me kind of blow this up. So this is just a short video. I'm not going to show the whole thing, but basically he'll kind of explain what's happening, and I'll talk over him because
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. Start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. If I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also.
Okay, so I'm gonna pause that one there. Let me show you another one. Let's do this one. So this is from, what is this, MIT, I believe. So he's gonna do basically the same thing. So he has a coil down here that you can kind of see that's connected then to another ammeter, or what's also known as a galvanometer. And then he's going to take a bar magnet and basically move it in and out. And then I'll show you one more video of something similar, but not quite the same.
I come close to this conducting loop. Notice you see a current. I pull back, current is in the other direction. Now I will go faster so that the change of the magnetic field per unit time is stronger. More current. I go out fast, more current. So you see, it's the change of the magnetic field that matters. If I come in very slowly, which I do now, very slowly, you almost see nothing. And right now, the entire magnetic field is inside this loop. The strongest I can have it. Nothing happens because there is no change in the magnetic field. It's only when I do this that you see the current.
Okay, hold that one. And then one more I'll show for you. So this is at Penn State. So I'll let him explain what he's doing. So what he's doing is he is setting up harmonic oscillation. So we move all of our faces so you can see it's a little bit better. So basically he has a bar magnet attached to a spring, and then he's going to harmonically oscillate this inside of the coil, connected to the galvanometer. So you see as it's harmonically oscillating, back it up just a minute. You can see the current.
Second.
There we go. So harmonic oscillation, you can see the current, then switching directions with the harmonic oscillation.
Second, we'll take a small battery and connect it to the second coil and see that when we put electricity into the coil, it produces a magnetic effect on the hanging magnet.
Which we now know that is because when he connects it to the battery, that's running a current through the solenoid. The solenoid then creates a magnetic field along the axis. So what he's doing here is he has the magnetic or the bar magnet align opposite to the direction of the magnetic field of the coil. So that's creating an attractive force pulling it then into the coil. And then when he breaks the circuit, that takes away the current, takes away the magnetic field. So then it goes back to its equilibrium position for the oscillation.
Moves vertically. So now we'll connect the two coils with wire.
So now what he's going to do is he's going to take away any power supply, just like in those other videos that we just watched. So there's zero power supply. And what he's going to do is he's going to, again, harmonically oscillate the bar magnet inside of this coil here. That coil then is going to generate a current inside of the solenoid. That then is going to be connected to the other solenoid. So that current's going to flow to the other solenoid, causing current to be induced inside of this one, causing the magnetic field of the solenoid to kick on, pulling this one down or up, pushing it away, depending on what direction this one is doing. And then eventually what will happen is that this one will start harmonically oscillating exactly in phase as this one. Not quite the same amplitude, but you can see the harmonic oscillation.
And start bouncing the first magnet so it moves up and down at its natural frequency, producing electricity at that frequency. So the motion of the first magnet will be translated to the second magnet electrically, and we'll see the second magnet begin to move at the same rate as the first magnet because we are inducing electricity in the coil. The magnet doesn't just sit there, the magnet has to move.
So, get rid of those, bring you guys back up. So basically, what you're seeing in all of these is that there's always zero power supply, but what's happening is you can actually induce a current inside of a coil loop due to a moving magnetic field. Okay. So basically what's happening is, let's say here is my loop of wire. I'm just going to draw it as a rectangle in this case, right? And then if I bring in a bar magnet, say here's my bar magnet, so that this is the north side, this is the south side, so my magnetic field points then in this direction. By moving this guy, what you can actually do then is source a current to flow inside of this loop. Now, what the one video was showing is that, or actually almost all of them, is the direction of the current will actually change depending on how I move this guy relative to the loop. So if I move it in, I'm going to have current flow in one direction. If I move it out, my current then is going to flow in the opposite direction. The other things the videos did nicely is they also showed that the faster you move the bar magnets, the greater the current becomes, which also means that also the number of coils that I have also gave a bigger deflection because I had more and more amount of current. So what's actually happening here is I have a changing magnetic field, which then induces a current. But remember, to have a current, I have to have a potential, because here I have a wire. That wire has a resistance, and Ohm's law says that I have to have a change of potential then is equal to the current times the resistance. So what's actually happening is by me moving then the coil, you're actually creating a potential difference inside of the coil due to the motion of the magnetic field, which is then inducing a current. Right? This is what's known as Faraday's law. So what Faraday's law is basically saying is that you can induce a current, i.e. an EMF inside of the wire by a time-changing magnetic field. But if you think about the magnetic field of the bar magnet, though, you're not actually changing really the magnetic field of the bar magnet, because the bar magnet has a fixed constant magnetic field. So what you're actually really changing is the number of magnetic field lines which pass through this wire or through this coil. Because again, if I think about, here's my magnetic field lines, which are actually penetrating out in this direction. Let's draw a couple of them, doing say something like this. So initially, if this thing is say moving down in this direction, so this is my velocity v, initially say I have two magnetic field lines which are penetrating through this loop. But if I draw another later time, so that my bar magnet now has moved much closer now to the loop. So my bar magnet now is sitting here. And I draw my same magnetic field lines. What's happening now is I have more magnetic field lines which are penetrating through the loop. So in this case, I now have 4 magnetic field lines which are actually penetrating through the loop. So what's more important is not the fact that the magnetic field itself is changing, but the magnetic flux through the loop is actually changing. So what Faraday's law says is that we can induce an EMF inside of the loop by having a magnetic flux changing inside of the loop itself. So this is Faraday's law. So Faraday's law says that E here, which is the induced EMF inside of the loop, is then equal to minus the time rate of change of the magnetic flux. Right? So here, the magnetic flux is equal to the integral of the magnetic field dotted by then the differential area. So here, this is not a closed loop integral, not like over a 3-dimensional object like we did with Gauss's law. This is then just through a 2-dimensional surface here. Okay. So this is what Faraday's law says, is that we can actually induce an EMF based on the fact that we have a time-dependent magnetic flux. Okay. But remember, to have an EMF, I also then have to have an electric field. So what Faraday's law is overall saying, and we'll talk more about this actually tomorrow, is that what's really happening is I'm inducing an electric field inside of the coil, which is then inducing a potential, so a change in potential, which then induces a current. So this is what Faraday's law is actually saying. So what Faraday's law actually says is that a time-dependent magnetic flux or time-dependent magnetic field will induce a power supply, an EMF, but an EMF is the same thing as an electric field. So you're actually inducing an electric field, so you can actually create an electric field from simply a time-dependent magnetic field. So this is actually Faraday's law. Okay. Now, the negative sign out here has its own name to it, and its own interpretation, and this is what's known as Lenz's law. So Lenz's law is the interpretation of this negative sign, which is an interpretation on the direction of the induced EMF, which is an interpretation of the direction of the induced current. So what Lenz's law says is that the current is induced in such a way as to oppose the changing external flux. So the current is induced to counteract or to oppose the changing external flux. So what does that mean? So what that means is that the loop itself, the coil, which now has a current flowing through it, that means it creates its own magnetic field. That induced magnetic field, which is induced inside of the coil, is induced in such a way as to change the changing external magnetic field. Okay. So what does that mean here? So what that means is if I go from this picture to this picture where I have the velocity going down in this direction, what's happening here is that the external magnetic field is increasing as it's pointing downward into the coil. The coil then doesn't want the external magnetic field to increase. It wants to keep it constant. So it's going to induce its own magnetic field. So this is going to be the direction of be induced to counteract the increasing external magnetic field. Right-hand rule number 3 then says the direction of the current then goes, if I curl my fingers in the direction of the current, my thumb then points in the direction of the induced magnetic field, which means in this case, my current must be flowing in this direction. So this is going to be flowing then in the counterclockwise direction. And this is then the induced current, which is induced due to this changing external magnetic flux. Now, let me talk about one more thing and then I'll let you go for the day. What happens if I move it the other direction? So let's say, again, here is my loop of wire. I'm going to take that same bar magnet, but I'm going to move it in the opposite direction. So initially, my bar magnet is here, and I'm going to move it upward with the velocity pointing upward in this case. So in this case, velocity is V in this direction, V this direction. My magnetic field here is pointing downward. External magnetic field is pointing downward. So in this case, what's happening is the magnetic field still points in the same direction. It points down, but it's decreasing because I'm moving it away, which means the flux is actually decreasing. So in that case, Lenz's law says, well, I have to induce a magnetic field inside of the coil, which is in the same direction as the decreasing magnetic field because I don't want it to get any smaller. I want it to stay the same, which means by right-hand rule number 3, we curl our fingers around in the direction of the current. Our thumb points downward in this case, which means our current actually moves in the opposite direction, which means in this case, it's going to move in the clockwise direction. Okay. So this is Faraday's law with Lenz's law. So Lenz's law is the interpretation of the negative sign, which tells us the direction at which the potential or the current is going to be induced, or overall the direction of the electric field. And Faraday's law says, well, what we're really doing, again, is inducing an EMF on the inside, where that EMF is negative the rate of change of the magnetic flux. Now, one thing you should point out here is I'm pretending here there is only one loop. If I have multiple loops, what happens in that case then is Faraday's law becomes minus the number of loops times the time rate of change of the magnetic flux. So tomorrow, we'll start off here. We'll talk about the different ways that I can actually then create an EMF, where I can either move this guy, move the area, or I can wobble around the angle between the two. So we'll talk about those tomorrow, okay? So this is Faraday's law. So again, this is what we call Faraday's law. So Faraday's law then is a relationship between the induced EMF and the time rate of change of the magnetic flux. So again, what's important here is not necessarily the rates at which the magnetic field is changing, but the rate at which the magnetic flux is changing. Okay, so we'll talk more about this tomorrow. So kind of quick introduction, but everyone okay? Any questions at this stage so far? Not so much? Okay.
About that, I got one about the group assignment whenever.
Oh, sure. Yeah.
So somehow I keep getting 0.0032.
Yeah, so it should be -3, not -5. That was a typo I made like 3 years ago that I tell myself every semester I'm going to change. And I just have to do that, so. Yeah, so no, what you have is correct. Yeah. Yeah. I said every semester I tell myself I'm going to change that, and then I just never do. So yeah, it's fine. One of these days, though, I'm actually going to surprise myself and do that. So it'll be great. So good. Any other questions anybody has? Like I said, we'll pick up from here tomorrow, and we'll talk more about this and all the different ways this can happen. So, everybody's okay? Sounds good. Okay. Have a good day, everyone. I'll see everybody tomorrow. Hopefully you'll be less sleepy tomorrow, more kind of attentive and all that kind of good stuff. Like we go. All right. See you tomorrow. Bye.